Now let's look at what happens with rotations. We will only be dealing with rotations about the origin. When it comes to other types of rotations, that's more at the high school level. Let's say our original point is at the coordinates 2, 5. If we try to do this with rotations using a circle on the graph and leaving it in the same position, that's going to get pretty complicated. It's going to be very difficult for students to figure exactly where they end up after a rotation. So here's an idea. This is a lot easier. It's a lot less confusing. It's best to just take your whole graph paper and just rotate it. In essence, you're going to be changing the positions of the x and the y axes, but it'll be very easy to tell exactly what happens after a certain rotation takes place. So let's do that. Let's say we're going to rotate 90 degrees counterclockwise, and that's what the little CC stands for. Okay, so let's just take our paper and rotate it 90 degrees in a counterclockwise direction. And here's where we end up. So let's see what our values are for our coordinate now. Okay, looks like we would have to go 5 to the left and up 2 to be in our new location. So that's what happens with a 90-degree rotation counterclockwise. Now let's keep going. What if we go another 90 degrees for a total of 180-degree rotation in a counterclockwise direction? So let's do that. Okay, so in essence, we've actually switched the location of the x and the y axis again. So let's see, where are we? Okay, we go 2 to the left and 5 down. So we're at the point -2, -5. Now let's do a little bit more in the counterclockwise direction. Let's go another 90 degrees so that it'll be a total of a 270-degree counterclockwise rotation. So let's do that. Let's just rotate our whole graph paper around. We stop here. We figure out that our new coordinates are 5, -2. But let's not stop there. That's just going in the counterclockwise direction. Now let's try clockwise. So let's start over again with our original location for our point being 2, 5. And now let's go 90 degrees clockwise. So let's do that. So here we are. Let's figure out our new location. We went 5 to the right and down 2, so our new coordinates here are 5, -2. Let's keep going. Let's go another 90 degrees for a total of a 180-degree rotation clockwise. Figure out our new coordinates. They will be -2, -5. And one more time. Let's rotate clockwise 90 degrees more. Here's our new location, 5 to the left and up 2. So our 270-degree rotation clockwise had us end up at -5, 2 for the coordinates. Now let's double check ourselves. Let's see what happens, and let's try to see what things we might have in common and whatever patterns we might have. Well, let's see. If we look at our original coordinates of 2, 5, there's a similarity between a 90-degree counterclockwise rotation and a 270-degree clockwise rotation. Well, let's see. Let's say that was our starting location, and let's look at what these actual rotations would involve. Let's see. If I start there, and let's take our 90 degrees counterclockwise. So we start here, we go 90 degrees counterclockwise, and we end up here. So for the second option, 270 degrees clockwise, so we start here, and we go clockwise around to here, and we end up at the same place. So that checks out. There's a commonality here. It looks like we have the exact same thing if we go 180 degrees counterclockwise, or if we go 180 degrees clockwise. Now that makes sense. But let's double check it to make sure. Here's our starting point. So if we go 180 degrees counterclockwise, we start here, go 180 degrees, so we'll end up here. And then if we start here and go 180 degrees clockwise, yep, we'll be in the same location. So that one makes sense. It looks like we have this pairing here. We started off with the coordinates 2, 5, and we ended up with coordinates 5, -2. So let's check that. Okay, here's our starting location. Let's see, let's try going 270 degrees counterclockwise, so it would be like so. We end up here. And then we start here and we go 90 degrees clockwise. Yes, we end up at the same location with either one of those rotations. If we let our original coordinates be x, y, what is the pattern here? Well, let's see. For our 90-degree counterclockwise and 270 degrees clockwise, these are our new coordinates. How do they compare to the original? Well, it looks like our x-coordinate here is now the y-coordinate after that rotation. And our new x-coordinate is what used to be the y originally, and it's also the opposite sign. And if we examine the numbers as to what happened here, that is in fact the case. Let's look at this pairing, 180 degrees counterclockwise or 180 degrees clockwise. Well, it looks a little bit simpler here. It looks like the x and the y coordinates stayed the same as far as the actual numbers, but notice that in both cases it's the opposite signs. Okay, so that makes sense. So if the original location has coordinates x, y, then with a 180 degree rotation, either clockwise or counterclockwise, you'll end up at the opposite of x and the opposite of y for your new coordinates. And let's take this third pairing. What happened here? Let's see, we have 5s for the x's, we had 5 for the y over here. So, okay, so now what happens here, my x-coordinate is now what used to be the y-coordinate. And then for our new y-coordinate, it's what used to be the x, and it's also the opposite sign. Let's see if this works. Let's try this with some type of geometric figure. So let's take our graph, and let's say this is the figure. It's a triangle, and here's the coordinates. So these are our originals. Let's say we decide to do a 90-degree clockwise rotation. So we do that. Now what we need to do is figure out our new coordinates. And so here they are. There would be 4, 5, 4, 8, and 10, 2. Now let's compare that to the original. Well, let me see. Here, the original x is now our y-coordinate, and it is the opposite sign, so that makes sense. And then the y-coordinate originally was 10, and our x-coordinate over here is a 10, so that makes sense. Our x-coordinate now is what used to be the y originally. Let's compare, let's say, the -5, 4 original starting point. What happens here? The new y-coordinate, it is the opposite of the original x, and then our x-coordinate for the new location used to be the y-coordinate over here. If we examine this other set of points, the -8, 4, the exact same thing happens. So this is valid as far as the generalization. If we're talking about translations, rotations, and reflections, note that in all of these, the only changes involve the position and or the orientation of a geometric figure. The measures of the angles and the sides remain constant. There was no changes in size or shape. Now let's look at dilations, and that's a little bit of a different animal. Dilations differ from the other listed transformations Although shape is preserved, the size of the new figure is different due to the changes resulting from multiplication by the scale factor. So again, the shape is going to be the same. It's not going to change at all. But the size is what changes. It's either going to be a larger or a smaller image of the original. Mathematically, the way that we would say that in much simpler fashion would simply be that the resulting figure from a dilation will be similar to the original. Of course, similarity simply says that you would have the exact same shape, but not exactly the same size. Let's look at what happens with the dilation, and of course we need to connect that to the idea of coordinates. Let's start off with this triangle ABC. Let's figure out and label our coordinates for each of the vertices. Let's say we want to do a dilation and our scale factor is 2. So what we need to do is simply multiply the x and the y coordinates of each of those vertices by 2. So we take our original vertex A and we multiply both x and y coordinates by 2. We get the new location A prime being 610. For our B, if we multiply again everything by 2, we get the new location for B as 12.4 for the coordinates. And then for C, double the x and the y, we get 22.14 for that new location. Connect the vertices, and here's our new triangle, triangle A prime, B prime, C prime. Earlier we talked about this idea of the center of dilation. It's not mentioned anywhere in this standard, but it won't hurt to maybe go ahead and lay the foundation for this so that we don't wait till high school to do it. What makes this a lot simpler and really not that complicated is that our center of dilation is the origin. So that really simplifies things a lot. So here's what happens. If we start at the origin and we draw a line that goes through our first vertex A and we keep it going, it's going to also go through the new vertex A prime. Same thing happens here. When we draw a ray that goes through B, it's going to go through the new location B prime, and the same thing with C. Now here's where the scale factor comes in. The scale factor was 2, so what's going to happen is that the distance from the origin to A prime is in fact twice the distance as it is from the origin to A. The same thing here. This segment to C prime from the origin is going to be twice the distance as the segment from the origin to point C. And the same thing happens with the segment that is drawn from the origin to B prime. That will be twice the length as from the origin to point B. Let's try a second example. Let's do another dilation. This time let's go with a quadrilateral, ABCD. Here's our coordinates. Let's go in the opposite direction. Let's have a dilation that makes the original figure smaller. Let's say our scale factor is 1/3. So just like before, all we're doing to get the new coordinates is multiplying all of our x and y coordinates by 1/3. So for our A coordinate, our new one will be A prime. We divide both of those by 3, so we get the 0.14. For point B prime, we divide by 3 again, which is of course taking 1/3. So we get 2, -1. Our new C coordinate is 4 2/3, 2. And then for the new location of point D, that's going to be 3 for the x and 3 2/3 for the y. Let's connect those to get our new figure. And sure enough, it's the exact same shape and everything, but it's definitely a different size. Just like before, our center of dilation is going to be the origin, which makes things a lot simpler. Let's start at the origin and draw a ray that goes through both the new location and the original location of our A vertex. Let's do the same thing for our point B. Let's do it for vertex C and C prime. And let's also do it for D. If we were to compare the respective distances to the new locations for the 4 vertices, being that the scale factor is 1/3, each one of these distances from the origin will be 1/3 as much as the distance was to the original locations. Again, the reason is because the scale factor is 1/3. The idea of dilations is relatively new probably to most students and even to some teachers. So it's real important that we get these basic facts down. But again, it all connects back to the idea of similarity. We're going to have the exact same shapes of these figures, but the sizes will change. And of course, that is determined by our scale factor. And as you can tell, it would be a very easy connection to the idea of proportionality. If we look at our standards for mathematical practice, by doing the activities that are involved with this standard, students would reason abstractly and quantitatively. They will construct viable arguments and critique the reasoning of others. If we look at the remaining standards for mathematical practice, by doing what's involved with this standard, they will use appropriate tools strategically. Of course, they do need to attend to precision, as you could tell. And last but not least, they will look for and express regularity in repeated reasoning.